Thank you for joining us. So my name is Zak Hassan, and I'm here with Diane Feddema. We work at Red Hat in the Emerging Technology Group on data analytics. I've been at Red Hat for the past 4 years. Our project is RAD Analytics, which is a platform where developers build data science applications on our Kubernetes offering, which is OpenShift. Along with building the platform, I also develop intelligent applications to do things like image recognition and other machine learning AI type of workloads.
And I'm Diane Feddema. I've been doing big data work for about the last 5 years at Red Hat. I started out working with Hadoop initially for a couple of years, and now I've moved into using Spark. And I primarily analyze performance data. I run experiments, collect that data, and then use the machine learning algorithms in Spark to analyze them.
So today we're going to spend the next half an hour to talk about the story of how we set up Prometheus to monitor our Spark cluster and are running Spark jobs live in Kubernetes pods. We'll dive into high-level concepts. We'll look at code. We'll actually show you a live demo with Grafana, Prometheus, all running in Kubernetes, our OpenShift offering. So we're also going to do some slight code changes, and we'll show you performance improvements of code, and then we'll run a job with the not being tuned, and then we'll run a job that's tuned, and we'll show you some performance improvements and quicker runtime. So our goal for building the platform was actually, when we built the platform, our goal was to try to improve the runtime of applications, to allow data scientists to do more rapid experimentation, to provide, if you write a program and you get quick feedback, rapid feedback, then you can do more experiments. And also when you're doing integration testing, you can do more ambitious testing when you know exactly how much memory, CPU, and whatever resources that are being consumed in Kubernetes. And one of the compelling reasons for even using Spark for developers is actually because of its parallel processing, its in-memory pipelining, and data end-to-end optimization. So our story, basically, this whole experiment, I started looking at this experiment last year, like around mid-June. I looked at, since we were running Spark in containers, I looked at what if we put an agent in there and then expose the metrics. And then, at first we were using Jalokia, and then later we decided to use Prometheus endpoints. Later, as the experiment continued, we created a CRD, custom resource definition, with a Spark operator that's able to deploy Spark cluster, discover the workers and the master, and then dynamically configure the targets to be consumed by Prometheus. We set up alert manager, and that wasn't enough. Actually, we tried to even do further optimization where I got in contact with Diane, and we set up. Diane helped actually set up the Grafana integration with Prometheus, and we were off to experiment on tuning actual Spark jobs. So this is not going to be an introduction to Prometheus. This is going to be more of actually using Prometheus. So if that's the talk, this is the talk for you. So I'm going to briefly go over what Prometheus is. Who does not know Prometheus? Okay. So Prometheus is a monitoring solution, and it is it's a time series database, so it collects the metrics running in your application. And you could either instrument your application, or you can use an exporter that would export out, like if you have JMX metrics being exposed, then you can use JMX exporter, or there's different exporters for different tools in your infrastructure. Luckily, if you're using Kubernetes, that comes out of the box, already So what's Spark anyway? So Spark is actually a data processing engine. It's parallel processing. It lets you spread your data across many machines. You can do in-memory processing, and it has optimizations to perform queries, machine learning, stream processing workloads, and more. You can choose to run it on Yarn, Mesos, or standalone. So for our setup, we're using standalone. There's actually some interesting work that's happening at Apache Foundation. Our group and other companies actually are working together on using Kubernetes as the cluster manager. Talk to me offline if you want to know a little bit more about that. So this is actually the building blocks of Spark itself. So you have the core, Spark core. Then you have different APIs and libraries that you would use for whatever particular problem you were trying to solve, right? So you can use SQL if you want to query the data spread across your cluster. You can use machine learning. You could use Graph. You can use streaming. If you have data that's being streamed into a Kafka topic, then that's one option as well. And you can actually access your data from different data sources. So you can access from HDFS, Amazon S3, Ceph S3 if you want. And you can write jobs in Java, Python, and Scala. I think some people also use R. How many people here use R? Okay. So RDDs is one concept to understand because that's the foundational thing within Spark. So RDDs are resilient distributed data sets. And basically your data is split into partitions and it's spread across a cluster. And then it's like basically you have a collection of rows that sit on a physical machines, and you have this concept of executors that execute your work, and these executors are actually in the Spark worker. So you might think, okay, why do I even need partitions? Interesting thing is you need partitions because when you execute work, if you have only one partition and you have 1,000 executors, your parallelism is only one. If you have 1,000 partitions but only one executor, same thing, parallelism is only one. So you want to have more partitions and more executors. And we're going to go into a high level of what a Spark cluster is made of. So Spark application, as I mentioned before, a Spark application is basically you get data from a source, right? Let's say HDFS or let's say S3, and then you have a Spark job. You write a job, so you have to decide if your job is going to be streaming or if it's going to be a job that's just a batch job. Either option, you could use the libraries that come with Spark. And then you want to store your data somewhere. If you want to train a model, you might want to store that model somewhere. And one thing that I mentioned earlier, remember that point when I said why Spark is popular? It's because of its parallelism, right? It's lazy by default. Its core data structure is immutable. Let me actually explain that. So what it does is it performs a transformation, but only until the very end when an action is actually called on it. So internally, Spark builds up a DAG, and it makes a plan for the transformation, and then it applies that transformation to the source data and generates a result. So under the hood, it actually uses RDDs. Remember that term that I mentioned, resilient distributed data set? But what you can do, there's a library on top of that called data frames that makes it super easy, like a little bit more simple to use. We'll talk about that more. So this is our setup within Kubernetes. We have pods that you're familiar with. We have containers that are running inside those pods. And these containers have a Spark master, a worker, and you can have more than one worker. And then the application that's running, it's running as a driver application. So I want you to remember that term, the driver. The driver is basically running, actually doing the job, right? So we use source to image to, when you have Git source code, you point to the Git source code, we pull down the image, it builds an image, and then it deploys a job. You're going to see all that stuff in the live demo. So some interesting metrics that we got back from the driver is things like block manager, things like the DAG scheduler, things like JVM and some of the internals of what's happening within the JVM inside the container that's running. And we found some interesting details. So this is just a high-level view of the cluster. So Prometheus is going to go and scrape these endpoints. So we have Java agents running in the Spark master and worker, and also on the actual driver application that's running. It's all running in Kubernetes. So we get information about the executor, how much memory is being used. We can get more information about, how much memory is actually being used by the whole Kubernetes cluster and other different details as well. But the thing is, you set how often you want it to scrape. So I'll explain that part in a later slide. So this is basically just when we're building a Docker image, this is the Java agent. Who is familiar with Java agents? Who has used a Java agent before? Okay, so 10% of the room. Okay, so Java agent, you pass a -Java agent at runtime when you're running the worker or the master, and you can pass it a jar, and that jar is going to, for this particular example, that jar is going to go and look for JMX metrics and expose it over REST in a format that Prometheus understands. So some prerequisites, you have to have JMX enabled. So this is a view of, we can see the network, CPU, memory of Kubernetes. We can see application metrics. And we actually, interesting thing is, we actually ran OpenShift Ansible to set this up, which is on GitHub. And then we had to do a little bit more experimentation for the Spark side, and we'll talk about that more. This is the configurations for an example of configuring something to scrape an endpoint in Prometheus. This is an example of a simple, very, very simple alert rule. You can set different rules, and then you would use promptql. So if you see the up equals 0, that means if any of these nodes that are being monitored, if they go down, I want to get notified, an email, Slack notification, or whatnot. PromQL. PromQL is what we use when we want to do visualizations, and Diane has some visualizations that she's going to cover. So just remember, gauges are like, when you're driving a car, gauges tell you how fast you're going, right? So that's a gauge. In Prometheus, you have gauges. And then there's something called counters. Think of that as an odometer, how many miles you've traveled so far. So without further ado, I'm going to pass it on to my teammate, Diane Feddema.
Thanks, Zach. Okay, so for the second part of the presentation, we're going to talk about how Prometheus and Grafana can be used when you're doing performance analysis, which is what I do in my job. So there are a number of things that you do get with Spark out of the box that tell you what's happening with your Spark job as it's running. But there are many important things that you want to know that the Spark web UI does not tell you. And that's what we're going to get from Prometheus and Grafana. Really important things that help you not get out of memory errors when you run your job, that help you tune your job. It just sort of turns the lights on and you suddenly know all the resources that are being used for your job. So we want to know things like how much memory are my workers and my master using? How much memory is available on the entire system? Someone else might be running at the same time as you. Is the network being saturated by my job? And what might I do to eliminate that bottleneck? What's the CPU usage on the container level, on the pod level, and on the node level? With Prometheus, you can look at a per node level for all these metrics. You can also look at a per application level for all of these metrics. So we, as Zak said, added these endpoints in Spark to scrape, and we're also scraping for Kubernetes to get all this information to help us tune our job. And there are just hundreds of metrics that are being saved in this time series manner. And we can't really go into all of them in this format, in this presentation, so we are going to concentrate on memory usage and the duration of the job. So we're going to show some example code, we're going to do some tuning, and we're going to improve the memory usage and the timing for the job. So efficient memory use is important for Spark, but it's also important for any data-intensive system. So when possible, we want to keep as much information as we can near the processors, and we don't want to spill to disk. We want to avoid spilling to disk with Spark jobs whenever possible. And we want to figure out what we want to cache. These RDDs that Zak talked about earlier, they're often costly to compute, and so we want to cache them instead of having to recompute them. So if we have multiple stages in our job, we want to cache the RDDs between the stages. So we're going to create Prometheus and Grafana dashboards, what we already did, and we're going to demonstrate them to you and show you how that helps us tune our Spark job. And it's actually really fun to create these dashboards. I mean, sometimes I forget that I'm actually working when I'm doing this. It's just a lot of fun to create these Grafana dashboards with the input from Prometheus. So Spark is an in-memory compute engine. It very aggressively uses memory. And even though these nodes that we're going to do our demo on have 256 gigabytes of memory each, so a cluster can easily have a terabyte of memory. There's still contention for memory, and it's still worth tuning your memory because these large analytics jobs very aggressively use memory. And in a Spark job, you can easily have 100 gigabyte heap spaces, so it's worth it to tune that. And we'll talk about how to optimize that for overall performance improvement. So now I'm going to talk a bit about Spark's memory management model, just so you'll understand why our tuning helps once we employ the tuning we're going to go with here. There are two memory usage types in Spark, execution and storage, and they share the heap space. The execution memory on the left here, oops, here we go. No, the animation didn't start yet. Execution memory on the left is used for short-lived results. It buffers intermediate results that your computation is performing. So for instance, in our example code, we're going to do a group by. In order to do a group by, you have to create a hash map, and you have to build that hash map somewhere. It's going to get built here in the execution side of the heap. And after we have performed this group by, the result is going to be an RDD, this resilient distributed data set that Zak was talking about, and it is going to be stored over in the storage side of the heap. So here's a little example of your code running, and the sharing of the open space here in the middle is space on the heap that's available. So the storage area, say you're caching, you put .cache on at the end of a bunch of your Scala or Python lines of Spark code, and you want to cache a little bit more of your data. So do you suppose this, what do you think? Do you think that you're going to be able to put this block here? Yes, there's open space, we're going to get to do that. But once we have contention, we have to decide which block is going to be evicted. And what happens is, the execution side always takes precedence over the storage side because the processes that are relying on this intermediate results that are in the execution side would fail if you were to evict their blocks. So that just forced some storage memory to spill to disk, which is okay. Sometimes people over cache anyway, and it's no harm. You can just reload what was in the cache earlier. Again, the execution side is going to take precedence. It's going to cause this to spill to disk. But there is a limit that you can set, and we can tune it, and this is something else we can view with Prometheus and play with this value. The user can set this Spark memory storage fraction, and that is the unevictable part of the storage memory. So again, execution takes precedence over storage up to a point where you have unevictable blocks. So one more thing I want you to understand is some APIs we're going to use, so when you look at this example code, it'll make more sense. Spark SQL is essentially a library that sits on top of Spark Core, and it gives us 3 additional APIs. It gives us Spark SQL syntax, so if you're accustomed to using relational databases, you can make SQL calls and interact with Spark that way. It also gives you data frames, which we're going to use in our example. And data frames are similar to a relational database table with named columns. It also gives you data sets, which are similar to data frames, but the columns are not named. Additionally, so we're going to use the data frames. Additionally, you get 2 back-end optimizations as well. And this is where Spark SQL sits in the stack. And in your user code, you can intermix the use of Spark API and Spark SQL API. So we are going to do a performance optimization. We're going to show a non-cache version and a cache version in our live demo. You need to figure out how much space your RDD takes. So this is something the Spark UI will tell you. You put .cache in the end of the line that creates your data frame. Then you run your job. You bring up the Spark Web UI. You go to the Storage tab, and you see the size in memory that your RDD is going to take. So then you're going to set that storage, unevictable storage region to be at least as big as all the RDDs that you want to cache. So this is our code. This is the before. We create these data frames. We do a cross join, which is a Cartesian product, and then we do a group by operation. And because we reuse an RDD in that group by, we want to cache it. So in our improved version, you just put .cache at the end of the line. That's going to cache those RDDs. And we're going to see what that looks like before and after in our timings and in our memory usage. So this is the query plan on the left for the non-cache version. You see that that's creating those RDDs, but they're not in memory. On the right, it shows that those are in-memory tables because they've been cached. So this result you're going to see in the demo as well, but just as a preview, we looked at all this running in Spark. We look at how much memory is being used with viewing it through Prometheus and Grafana. And the result is that after our optimization, we went from about 5.3 gigabytes per worker to around 2 gigabytes per worker after we cached that RDD. So this is my relative index of performance that I use in my performance metrics, but here it's the same value as a percentage change, so I'll just explain it as a percentage change. We got a 76% improvement in memory usage, so that's memory reduction, and we had a 10% decrease in runtime by adding that optimization. Okay. So, demo time.
Talk about this.
Okay.
So this is Grafana, and Diane's going to show us running a Spark job, and
Okay.
you'll see.
Go ahead.
You'll see how performant it is. So
first we see here that there is no Spark job running. And I'm going to go to my deployment configs. I'm going to go to my non-cached version. I'm going to deploy this non-cached job. Then I'm going to look at the Spark master. We should see this job showing up here. Take a second. There it is. There's our non-cached Spark job. We can see that it's running. We can see here under the storage tab that, in fact, there is nothing because we haven't cached anything. Now we can go over to Grafana, and we see that it's going to start, the job is going to start showing up here soon. Here it is. So we see our CPU usage going up. To start with, we just have like we see that the network is quiet. The whole system is pretty quiet. But as this job comes in here, we're going to see our memory usage going up. Let's just go and make sure that that job is still running. Yeah, it's running. Okay, that's good. It's all good. All right, so
Yeah, so now it looks like it's starting.
So you see that the cluster CPU usage is going up. You see the memory usage is going up. Pod CPU usage. Okay, so now what we're interested in here is, can you see that? Let's see.
It's visible.
Can they read the numbers, you think? Yeah. Okay, so so you can see that we've got 5.2 gigabytes for these 4 top entries here. Those are our Spark workers. This is the non-cached version, okay? And there is only 1 pod per container, so the pod metrics are the same. And down here at the bottom, we have our JVM pools. We have the Eden space, the survivor space, and the old gen space, which is, the Eden space is where our new Java objects are being created. After the first garbage collection, things get moved over to the survivor space, and then our cached items and things that make it through another garbage collection are going to end up in the old gen space. So we can use these Grafana dashboards at the bottom here to optimize how we're going to use the JVM for these Spark workers and the Spark master. Now we see we're up at 40% of CPU usage for the cluster, and that's because that Cartesian product is happening right now. It's very CPU-intensive operation. And you can see our 2 nodes here that are sitting in Boston doing this work as we watch it. And so here we have the memory high water mark for the workers at 5 gigabytes, 5.5 gigabytes each. So now we'll go back and see if that Spark job is finished. I happen to know that it finishes in about 3 minutes there, 2.9 minutes, it finished. Okay, so now we're going to go back and deploy the cached version.
So if you notice there, Diane pressed deploy. So this is a deployment config, and when Diane was building her application, she used source to image to build an image, and then once Diane had her image, we used the deployment config to roll out the Spark job. And then when Diane wanted to rerun that same Spark job, she just had to press deploy, and it reran the same job.
Yeah, one of the challenges in making something that you can do in a 5-minute demo is you have to cut an actual Spark job into something that will finish in the amount of time that we have up here. So I've just submitted the cached version. Now we're going to look at storage. See, we have the 2 RDDs there that we've cached. That's running live right now. And now we can look over at Grafana, and you can see that last job, that drop-off right there, is the last job that finished. We're going to see the next job coming through.
So there's a little bit of a lag because we set the intervals a little bit with a little bit more time in between. So if you wanted to see more metrics a little bit quicker, then you would configure those things.
Instead of scraping every 10 seconds like we are.
So you could set to scrape every 10 seconds, or you can set lower. But
so now the second job is running. We've already hit the high water mark for the containers that are holding the workers. It's showing right here. Same for the pods, about 2 gigabytes each. Again, we can go down and look at our JVM pools. I noticed that the network was very quiet. Network is not an issue with this example at all, and there's no bottleneck there. But the important thing here is that these values were not known to us previously, and it's just a guessing game if you don't have these metrics to look at. So this is incredibly helpful when you're tuning a Spark job, and I'm sure applications in general. Just the fact that you can look at how it's load balanced across the nodes, then you can dive down deeper and see at the pod level and container level exactly what's happening. So that's it.
Yeah. Thank you. So we'll take any questions if anybody has any. We also have office hours for about an hour. We're going to be at the Red Hat booth. So if you want to stop by, ask any questions of anything that we showed up here, because everything that we did was all open source.
And reproducible.
And reproducible.
You can do it yourself.
Thank you.